Welcome to my video tutorial about the Arrhenius equation. After watching this tutorial, you should be able to perform calculations using the Arrhenius equation, rearrange the Arrhenius equation into its straight line form, y equals mx plus c, and finally use experimental data to determine the activation energy of a reaction. Arrhenius was actually a Swedish scientist, originally a physicist but often referred to as a chemist, and he was one of the founders of science of physical chemistry. He received a Nobel Prize for chemistry in 1903, and his equation has vast and important applications in determining the rate of chemical reactions and for calculating activation energy. In the Arrhenius equation, K is equal to the rate constant. A is the frequency factor. This is a measure of the rate at which particles collide. It can also be known as the Arrhenius constant and the pre-exponential constant. E is a mathematical constant, and just like pi, it also has a value. EA is the activation energy measured in kilojoules per mole. R is the ideal gas constant, and T is temperature in kelvins. In the Arrhenius equation, this whole part here, we can say that this is the exponential, and it measures the fraction of collisions with enough energy to react. We know from the collision theory that the rate of reaction is temperature dependent, but the rate equation doesn't really show this relationship. The concentration will remain constant no matter what the temperature. So the temperature dependence lies in K, the rate constant, and we know that if K increases, so does rate. When using the Arrhenius equation, you're going to need to use these function buttons on your calculator. You need to press the Shift and natural log button to get E, the exponential, and for some calculations you will be needing to use the natural log button itself. Okay, let's have a practice using our calculator. So I'm going to press Shift, natural log, and I'm going to type in 1. What do we think the answer might be for this? Oh look, it's the exponential constant, 2.71828. So let's have a look at the relationship between the rate constant and the activation energy. So as EA over RT gets bigger, the frequency factor, or the exponential factor, E, gets smaller. Okay, so let's try this out. So on your calculator, put E to the minus 10. What do we get? Well, you should get 4.53 times 10 to the minus 5. Right, let's make that smaller. Let's go to E to the minus 15. What do we get this time? Well, you should get 3.06 times 10 to the minus 7. So let's have a look at how EA affects K. Well, if we increase EA, it means the fraction of EA over RT would also increase, which makes the frequency factor E decrease, as we've just found out. And if E is decreasing, that means that K will decrease. And if K decreases, then rate will decrease also. We now know that as EA over RT increases, the frequency or exponential factor E decreases, and vice versa. Now if you increase T, that means the fraction of EA over RT will decrease, and therefore the exponential factor will increase. If E increases, K increases, and therefore rate increases. This is the mathematical way of showing that as temperature increases, rate of reaction increases. Now this part of the equation shows the fraction of collisions with enough energy to react. Remember the Maxwell-Boltzmann distribution curve? Now imagine a reaction with an activation energy of 50 kilojoules per mole. Now as an exam tip, whenever you solve Arrhenius problems, you need to convert all units to joules and kilojoules. So this would be 50,000 joules per mole. What would the fraction of molecules with enough energy to react be at 300 K? Remembering that R is equal to 8.31. Okay, let's go through this on the calculator then. So shift, log to the minus 50,000 divided by open brackets 8.314 multiplied by 300 close brackets. That's the equals button there, 1.967 times 10 to the minus 9. This tells us that about 2 molecules in every 10 to the 9 have enough energy. So let's just add that to our Maxwell-Boltzmann graph. Okay, let's recalculate now, but we'll raise the temperature to 310 K. Once you recalculate that on your calculator, you come out with 3.76 times 10 to the minus 9. That's almost doubled as temperature increases by 10 degrees K. And if we put that on our Maxwell-Boltzmann, you can see that there is a greater portion of molecules that have enough energy. And of course this is what the distribution curve would look like if T was higher. This equation can be written in a non-exponential form using logging rules, which is more convenient and can be used to interpret graphically. First of all, it's done by taking the logarithms of both sides. Then we separate the exponential. Then we separate the pre-exponential terms. This can also be expressed in the following form. More importantly, so we can use this graphically, we use the following expression. Graphically, you will notice that this now looks like y is equal to mx plus c, where y is the y-axis, m is the gradient, x is the x-axis, and c is the y-intercept. So plotting it graphically, the y-axis would be the natural log of the rate constant k. The x-axis would be 1 over t, and don't forget that being kelvins. Then the gradient itself from the plot would be negative activation energy over r. And the point where the intercept meets the y-axis would be natural log of a. In terms of plots, it doesn't have to go through the origin 0. My final exam tip would be to remember that lowercase k is equal to the rate constant. Now this mustn't be confused with uppercase K, which of course is temperature in kelvins. Thank you for watching this video. I hope it helps.